So this is the lecture for experiment 7. I've been having some trouble with my recording software, so I'm going to split this video up into 3 parts. So, sorry, it's actually experiment 6. It's listed as 7 here. So I will post these as video experiment 6 underscore 1, 2, and 3. So if we look at just the title of the experiment, combinatorial chemistry, the synthesis of azo dyes, there's really 3 objects that we need to talk about, and so I'm going to split these videos up into a discussion of what combinatorial chemistry is, a discussion of what makes an organic molecule absorb light, and then finally we're going to talk about the synthesis of azo dyes. So any discussion of combinatorial chemistry really has to have at its root a discussion of drug discovery chemistry, because inherently combinatorial chemistry has its roots in drug discovery. And the reason for this is actually really quite simple, is that if you are going to try to design a molecule to inhibit a certain biological process, there has always been this fundamental question of what do you use as your source of molecules to as starting points for trying to inhibit this biological process. And really sort of the beauty of combinatorial chemistry is that if there is a certain class of molecules that you're interested in exploring, if you can devise a synthesis that can go along a combinatorial route, then you can generate hundreds, if not thousands, if not tens of thousands of molecules in really short order. And that, as it turns out, is highly beneficial when you think about the drug discovery process. So again, I don't want to spend too much time on this, but the first step typically in any drug discovery effort is screening of molecules against a biological process. You develop some biological assay, and then once you develop that biological assay, you're going to develop an approach to systematically screen hundreds, if not thousands, or tens of thousands, or even I've been involved with screens that go up to 100,000 molecules that are screened against one biological target. So in cases like this, you really need an efficient way to generate sources of molecules. So this is a oversimplified version of how you start out with thousands of molecules in a initial drug discovery effort, and then winnow it down into just a few, and just to a few examples that are going to enter clinical testing, and then that then winnows down into potentially one molecule making it into the clinic. So I think that, again, since we're talking about combinatorial chemistry, and we've already introduced this idea that in combinatorial chemistry that the roots of this are all in the medical field. I think that a good example of the early exploits of combinatorial chemistry can be seen in efforts to take cocaine and make molecules that still have the same local anesthetic effect of cocaine, but don't have all of the other properties of this molecule. So an important point to bring up here is I think that everybody has seen a movie from either the late 90s or the early 2000s where um, that there is a cocaine bust, and the officer that is instigating the cocaine bust will take a white powder and rub it on their gums, and they say, "Oh, that's cocaine." Well, how do they know that? Well, the reason for that is that cocaine itself is a very effective local anesthetic, and actually still used to this day in some eye surgeries. So the idea behind using combinatorial chemistry to develop new versions of cocaine would be to identify some central core unit of cocaine. In this case, we're going to talk about this central bridgehead nitrogen, and then develop a synthetic approach where we can systematically change these substituents around this bridgehead nitrogen. Or I think the better terminology here is change the building blocks around this this bridgehead nitrogen. And so we can see some early examples of this. The first clinical alternative to cocaine in the clinics was Novocaine or Procaine, and you can see that the synthesis that utilized that central nitrogen, then adding different building blocks around it, gave us Novocaine, gave us what is still currently used today as the major topical anesthetic, lidocaine, and then also further efforts led us to benzocaine, which is the most common over-the-counter local anesthetic. The second item that, if you're going to discuss combinatorial chemistry, you really have to touch on this idea of solid phase organic synthesis, because for the most part, most combinatorial chemistry occurs in the solid phase. So the solid phase that is most typically used is a polystyrene. So this is styrene. If you polymerize, this would be polystyrene. And then you functionalize this in ways that are very similar to how we functionalized ferrocene using the Friedel-Crafts acylation. Um, but again, this, I just want to talk about this in a very brief sense, because in order to really understand the power of combinatorial chemistry, you have to understand why this solid phase resin is so important. And so here, this is a figure from a paper that I wrote a few years ago that describes this idea of combinatorial chemistry, and it compares it to the types of chemistry that you're familiar with. And so the problem here is the same. How are we going to make 27 different molecules that have 3 differing building blocks? So if we use solid phase split pool synthesis methods, we would put our first building block on. We would pool all of those products and then resplit them, so that each time that we add the second building block, you'll get a homogeneous representation of building block 1, 2, and 3 from the first coupling. But then when we do this second pooling, you have a pool of 3, a pool of 3, and a pool of 3 for this second building block, either building block 1, 2, or 3. And then the same thing happens, that you have a pooling and a splitting of the molecules on the resin. And what you can see is that through doing 3, 6, 9 reactions, that you will get every single permutation of those 3 building blocks over those 3 reactions, which gives you 27 total molecules. So after 3, 6, 9 reactions, you'd have 27 molecules. In order to do the same thing with traditional synthesis, you'd have to have 3, 9, and then 27 reactions, totaling 39 total reactions to get 27 molecules out of this. And so if you can then extrapolate this, you can really start to understand the power of this. Let's say if you had 5 building blocks and you had 20 different you had 5 reactions and 20 different building blocks, right? So that would be 20 to the 5th power. You know, you could really start to imagine that you can make a lot of molecules very quickly this way. And these are shown in a little bit different format on the following slides, and I'm not really going to go into the details of this. And this gets us to our second video that we're going to talk about. And so this video will end, and I'll start the next one.